Right, okay, so hello everyone, and welcome to this short discussion where we discuss basically some articles in physics or mathematics or foundations of physics or philosophy that basically pertains to some issues that people usually are not aware of. Um, and today, what I would like to discuss, and perhaps we are going to study or look at more papers related to this, is what is called Hilbert's sixth problem. And this is talked about in a somewhat, well, not so recent anymore, but like 2018 special issue on Hilbert's sixth problem. And what I'm going to go through here is basically the introduction article of this particular problem. So kind of setting the stage for what is this, what's the story about this Hilbert sixth problem. Um, and then if you want, I will put the link, of course, in the description. You can have a look at this article in more details. It's perfectly accessible to basically anyone, I think. And also, basically, all the other articles, for most of them, at least I've tried, they are accessible as well for free. Um, so you can also have a look, and depending on some articles from this issue or from some other articles, we may probably talk more later about Hilbert's sixth problem. Um, okay, so this particular article is a sort of opinion piece introducing the topic, and this is by Gorban. And as I said, this was published in 2018 and the title is Hilbert's sixth problem, The Endless Road to Rigor. Um, now, let's try to understand a bit what this is about. So I don't know if you can see, I hope you can see on the screen, um, but this is basically something that was set up in 1900, and Hilbert presented a series of 10 problems. Okay, so that's what is written here. So there were 10 problems in mathematics that were, or yeah, in mathematics, or what you could call the mathematical science, um, that are now part of the 23 problems that are published later. And basically, there is a sixth problem which has to do with doing what David Hilbert wanted to do in mathematics, which was the axiomatization of mathematics, so defining everything, for example, from set theory, or doing things that were as nice, if you will, as like Euclidean geometry, but everywhere else in mathematics, including physics. And that's what basically the sixth problem is about. Now, let's look at the precise statement of the sixth problem. So the title, as formulated by Hilbert, was Mathematical Treatment of the Axioms of Physics. And the actual statement is the investigation on the foundations of geometry suggests the following problem: to treat in the same manner by means of axioms those physical sciences in which already today mathematics plays an important part. In the first rank are the theory of probabilities and mechanics. Now, as you know, I've talked quite a lot on this channel about probabilities, and in fact, the huge conundrum that physicists were kind of confronted to when they had to use probabilities in mechanics and in physics to try to explain the world around them. And there are some videos, maybe I will kind of put there here, that are related to the so-called ergodicity problem, which had to do with this particular aspect. Um, and nowadays, this problem is still very much open. How do we justify probabilities in physics? Now, the thing here is, as people call that, so from the point of view of philosophy of science, this is what is called a scientific program. And so what that means is that basically you've got a specific agenda that you want to basically succeed at. And so here, this is basically to apply some of the strategies Hilbert had at the time in mathematics and apply them in physics. So for example, um, there is here, as to the axioms of the theory of probabilities, it seems to me desirable that their local investigation should be accompanied by a rigorous and satisfactory development of the method of mean values in mathematical physics, and in particular in the kinetic theory of gases. Boltzmann's work on the principles of mechanics suggests the problem of developing mathematically the limiting processes there merely indicated, which lead from the atomistic view to the laws of motion of continua. Now, philosophically speaking, the reason why this is a fascinating problem is that on the one hand, it appears to wanting an axiomatization um, of physics, so simply that it's well defined mathematically. But from a philosophical standpoint, it seems to say something else, and that's why the sixth problem of Hilbert is very important for many, let's say, reductionists in physics, because as you can see in mathematics, let's say you want to frame all mathematics on set theory. Um, some people might say that it's a bit arbitrary that whether you ground your mathematics on set theory or something else. Um, but when it comes to physics, when you decide to axiomatize basically the the assumptions in physics and make it kind of like clear and concrete where you start from, etc., then if you're a reductionist, you would want to have things that are well axiomatized at the ground level, according to Hilbert, that is described by mechanics, and then somehow you want to have basically well formulated mathematical procedures that are going to tell you how you go from the atomic view onto things that are not atomistic anymore, and that basically are subject to the laws of thermodynamics, for example, or the laws of elasticity of material and stuff like that. So that's the kind of things that basically comes. So there's a philosophical underpinning and kind of package wrapping this up as well. So there are actually multiple interpretations of the sixth problem, of Hilbert's sixth problem. The most famous one and the ones that has been most worked on is actually to go mathematically from Boltzmann equation. So that's part of what is called the kinetic theory of gases or fluids, if you want. And you go from this Boltzmann equation, and then you try to derive from that by using a well-defined and kind of well-defined, well-behaved set of mathematical procedures that need also usually to be explained philosophically, like semantically, they need to be explained in terms of what do they mean, etc. Um, on how to go from this kinetic theory of gases onto the laws of hydrodynamics, which were already known at the time, and that would be to derive the so-called Euler equation in non-viscous fluids, or to derive, for example, Navier-Stokes equation of hydrodynamics. And basically this is a huge problem that people have started basically in the 1900s, and to this day this problem is not solved. So there is no clear and well behaved, and that does not seem ad hoc in parts and stuff, procedure or set of procedures that give rise to the equations of hydrodynamics as we know them and as we use them in basically in engineering, in everywhere, like in automobile, kind of aerodynamics, for airplane design and stuff like that. Basically, there is no well-defined bridge mathematically between the kinetic theory, so how the particles statistically behave as expressed by Boltzmann, onto this fluid dynamic behavior at a much kind of larger time scale and length scale level. Um, so that's a typical problem. That's what is explained in this paragraph. So there is this very famous expansion from Chapman and Enskog, um, and that's usually something that people learn, like maybe at a postgrad level or late undergrad level if they are into kinetic theory and statistical mechanics. And the bottom line is that this is still very much an open problem. And in fact, here, as they say, there was a media reaction on July from 2015 from Quantum Magazine saying that famous fluid equations are incomplete. So what happens is that some people try to solve that problem by saying that the equation we try to arrive at are actually not the right ones. And so that's why things are kind of messed up. So that's an interesting take. And again, there are loads of paper on that particular question or interpretation. Now, another aspect has to do simply with the description of probability. So let me get there. So probability, and that includes as well quantum mechanics. And so that's basically the thing that is interesting to us. So you see here, in this paper, the authors declare that the goal of an axiomatization of physical discipline consists of formulating the physical requirements so clearly that the mathematical model becomes uniquely determined by them. Like this, this is just amazing to imagine this is possible to state these things this way. And so one of the interpretation here is the first attempt at formalization of quantum mechanics. And this was indeed performed by von Neumann. And von Neumann, most people are not too aware of this, but proposed an axiomatic theory of probability, which actually was compatible with the probability theory of quantum mechanics and contained also classical probability theory. Now, history has happened, and nowadays when we teach probability theory, we only teach what comes from Kolmogorov's axioms that are mentioned here. That was from 1933. And so basically there is this kind of huge problem to determine the role of probability theories. What do they mean? What does they mean in quantum mechanics? What do they mean in classical kind of theory? Is it different in either case, etc., etc.? So there are plenty of things to look at here. Now, this special issue, what they say they are going to look at, and it's just to whet your appetite here, is basically look at axiomatization of classical probability, axiomatize the new, at the time, quantum probability, and clarify the connection between the two. So that these are things that are being explored in this particular issue. There are also things related to, as I said earlier, things related to the Chapman-Enskog things as well, so the fluid dynamics limit, and also things related to geometry as well, so connections with general relativity and so on. So I think that's about it. I just want to mention this here. Slemrod state that the classical Boltzmann to Euler limit fails in the most interesting cases. So there are situations, very kind of contrived, if you will, situations where these limits can be obtained. But when you want to obtain them in cases where you want to obtain them for actual fluid dynamic purposes and so on, then essentially things kind of explode in various places and so on. Mathematically, I mean. So let's finish here. So there is a philosophical discussion here. I'm going to skip that. I already talked a little bit about these aspects of philosophy. And just look at the conclusion here. There are three general lessons from the history of the sixth problem. Attempts at axiomatizing are useful even beyond mathematics. So basically that's what it means in physics. We need to clarify things so that basically we work on safe ground. But usually this clarification comes heavily with basically clarifying the mathematics. This order may be much more complicated and counterintuitive than the preceding chaos. So you see, they help to clarify the basic assumption and keep the mind in order, but then this order may be much more complicated and counterintuitive than the preceding chaos. So that's kind of the thing here that that's a cost maybe that we need to accept, and then the road to rigor is infinite. And I think this, could be felt as being discouraging for people who imagine that at some point we reach some kind of dead end and like everything is done and set. But no, and these people very optimistically say that this is neither encouraging, well, okay, nor discouraging. This is just the way it is. Okay, so basically, this is just to tell you a bit about this sixth problem, and again, some foundational issues in physics, and in particular, at least that's how I want to formulate it here, fundamental issues related to the, let's say, a reductionist program, like a rigorous reductionist program. Okay, so on that note, I might actually talk later on about some other take on this sixth problem. That was just to give a short introduction about it. If you've got any questions or comments, by all means, do let me know in the comment section. Okay, see you in the next video.